if you haven't watched the video about bounded and monotone sequences, please make sure that you watch it before you start watching this one. Otherwise, you're going to be a bit lost, and also this one contains some spoilers. Okay, so let's get started. Here we're going to show that if I know that a sequence is convergent, then it must be bounded. So the theorem just tells me that if the sequence an is convergent, then the sequence is bounded. So what we want to show is that my sequence is bounded. So let's try to write down what that means. Well, that means that there exists an A and B in the real numbers, such that all the terms of my sequence are dropped in between A and B. And well, what I know is that my sequence is convergent. That means that I know that the limit exists. I don't know what the limit is, but I know it exists, and I'm just giving it a name. I'm calling it L. So what I know is that there exists an L that is the limit. So if I'm expanding out the definition, what I know is that there exists a real number L, such that for every epsilon positive, there exists an n naught in the natural numbers, such that n greater than n naught implies that the distance between a, n, and L is less than epsilon. And to be able to see how we can go from what we know to what we want, it's very useful to take a look at a diagram. Here, I have a sequence, and remember what we said is that for any epsilon, if I know that my sequence converges, I can create an epsilon band around my limit L, and then all the terms of my sequence after a certain point are going to be trapped in that epsilon band. Like we can see here, we have these kind of brighter blue areas where all my points are trapped. And that happens for all the terms after these n, capital N or n naught. So, how can I use this? Well, you see here I have a finite number of terms that are not controlled by convergence, right? They're the ones escaping my epsilon band. And then all the other terms are trapped here. But you see, bounding a finite set is quite easy because I can just call them all, look at them one by one, and pick the biggest of them all and the smallest of them all, and then I'll be able to trap them right in between the biggest and the smallest. That is not possible with infinite sets because I cannot look at them one by one. So that is a big difference. So now we have a finite set. So what I'm going to do is I'm going to get the smallest of all those, the biggest of them all, and now you see we trapped my whole sequence now in between these A and B. Maybe we could have had that all the points were originally trapped in within my epsilon band and I didn't have to worry about those naughty points, but here I had those naughty points, so I had to handle them separately. So that is the idea. As you see, what we're going to do is convergence is going to let me take control over all the terms except for a finite number of them. But then these finite troublemakers are easy to control. So now let's try to write down a rough work of what we want to do before we write a nice, beautiful proof. So we want to find an A and B such that all the terms of my sequence are between A and B. And I know that there exists a real number L such that AN converges to L. So the idea is I'm going to use the definition of limit with epsilon equals 1. And remember, I said it before, here I can pick the epsilon because I am using convergence, not proving convergence. So I'm going to use the definition with epsilon equals to 1. And what this will tell me is that after a certain point n naught, all the terms of my sequence are within 1 of L. So the distance between my terms and L is just less than 1. But of course we can expand out this absolute value, and we know that that means that AN is between L minus 1 and L plus 1. And I'm going to rewrite the definition here, and I'm highlighting this part in blue because you see we know that AN is greater than L minus 1. So if I want to find an A that is less than or equal to all my ANs, it makes sense to pick an A that is less than or equal to L minus 1. And that takes control of lots of them, infinitely many of them, but we also need to get control over those guys that were before a naught. Well, we need a to be less than a1, a to be less than a2, and a be less than or equal to a naught. Then how can I make all these things happen? So I need to get a less than all these different quantities. Well, if I pick the minimum of all of them, then I'll be guaranteed that my capital A is less than all the quantities that I have here. And that is the idea of the proof. And then I will need to find my B. Try to think about how you can find B. What should B be? So maybe it's a good idea for you now to pause the video and try to think of how to define B before you continue watching the video. Great, welcome back. So now let's try to write down the proof. You see, we're going to assume, to begin with, that the sequence converges to L. And we're going to take epsilon equals 1 in the definition of convergent. Then we know that there exists an n naught, such that for n bigger than n naught, a n is between L minus 1 and L plus 1. And these are good. We're going to be using this, so let's put a label into it. But now I'm going to take A, the minimum between L minus 1 and the values of all the terms of my sequence that I haven't managed to control by using convergence. So all these first n naught terms, so we have it there. And then for B, well, we need to take the maximum between L plus 1, because that's an upper bound for the terms after n naught, and all the terms that came before I managed to gain good control of my sequence. Oh, very good. But you see, now if I pick a natural number, if n is bigger than n naught, then I know that, well, a is less than or equal to L minus 1 by the definition, and now I know that a n is bigger than L minus 1 because n is bigger than n naught. And a n is also less than L plus 1, which is less than or equal to b. Good, we use the first one. Now, if n is less than or equal to n naught, then by the way we constructed a and b, an has to be between a and b. Try to think about why. And that completes the proof. That's great. So we now know that if we have a convergent sequence, then it is automatically